Bonjour, and welcome to these office hours for week 5 of this course in functional analysis on Coursera. Today I am at the Jardin du Luxembourg, which is a park next to the French Senate, a very nice and well-kept park, tax heroes at work. And the castle behind me was built by the widow of Henry IV during the 17th century and is now the French Senate. If you come to Paris, I strongly suggest you visit this beautiful park, and if you can, depending on when you come, that you visit as well this beautiful castle. Today I would like to address 2 points, one question, one comment, regarding the, first of all, the Banach spaces, and second of all, the Lax-Milgram lemma. As you know, during this week, we talked, week 5, we talked about Lax-Milgram, which is a very important result. Thanks to Lax-Milgram, we can prove that equations have one solution only, and also that the solution depends continuously on the data, which is a very important fact when you actually look at the engineering behind the PDEs or the PDEs behind the engineering. Now, it was suggested that I discuss the size of a Banach space, and let me explain. Let me elaborate on this. And one of the TAs said I should prove that a Banach space never has a countable basis. And I would like, by the way, to thank him, and actually to thank both TAs, Anna and Caroline, who are doing an outstanding job. They're really working hard on this MOOC, and I would like to thank them very much for all the work they put in this MOOC. So back to this Banach space, it was suggested that I prove that a Banach space has no countable basis. As you know, a Banach space is a linear space or vector space which has a norm, and for which norm, with respect to which we have completeness. In other words, if you look at the Cauchy sequences, they will converge into space. Cauchy sequences will converge into space in the topology that comes from the norm. So if you look at a Banach space, again, it is, by definition, a vector space which is normed and which is complete. So it is a vector space. And as every vector space, it will have a basis. If you look at R3, it will have a basis with 3 elements. If you look at Rn, it will have a basis with n elements in the basis, and vectors in the basis. If you look at the set of polynomials, which we usually denote R of x with brackets, it will also have a basis. One example of a basis, there are several bases, but one example will be 1, x, x squared, x cubed, etc. And every polynomial can be written as a linear combination of the element of this basis. And there's only one way to write this linear combination for every polynomial of the space. The basis will be infinite, but it will be countable, because you have the same number of elements in this basis as the number of integers. Same numbers being, meaning actually that we have a bijection between the set of the element of the basis and n, the set of integers. In the case of a Banach space, I will state that the Banach space has no countable basis, which means that the basis of this Banach space will be so big that, well, number one, it is not finite, like R3 or Rn. It is not even countable, like the set of polynomials. It will be much bigger than this. And that's what we're going to prove now. So let me get started, and let me prove that if X is a Banach space, then X has no countable basis. Before we start the proof of this result, I would like to state the Bair's theorem, which is named after René Baire, a French mathematician born in 1874 in Paris, in the 6th district, actually not far away at all from where we are now at the Jardin du Luxembourg. And what René Baire proved is that in a complete metric space, any countable intersection of dense open sets is dense. And that in any countable union of closed sets with empty interior has an empty interior. So in a sense, what it means is if you have an empty interior, which means that you cannot insert an open set or an open ball in this set, then by doing a countable union of these sets, you're not going to add enough points, so to speak, so you will be able to insert this open ball in the union. So again, what we're stating here is that any countable union of closed sets with empty interior will have an empty interior. The union will have an empty interior. Okay, so we're going to use this Bayes' theorem to prove the result that we want to prove, which is that if X is an infinite dimensional Banach space, then X admits no countable algebraic basis. We will do a proof by contradiction. So we will suppose that there is a countable algebraic basis for X. So let's call it EI, and the index I is in the set capital N because it's countable. So capital N, as a reminder, is the set of all integers. Now for n and for non-zero n, we will denote by Fn the set of all linear combinations with the EI. So basically, this is the span of the EI for I in between 1 and n. So I'm only going all the way to n, from 1 to n, and that will be Fn, which will be a linear space, vector space, with dimension n. And obviously the basis will be the EIs. Now the Fn's are closed, but if they are all with a non-empty interior, then when I do the union of them, the countable union of them, then the Bayes' theorem will state that X has an empty interior. So, and that's not possible because X has a non-empty interior. So what I'm saying is that it's not possible for all of these Fn to be with an empty interior, so at least one of them will have a non-empty interior. So what I'm saying is that there exists an n0, at least one n0, such that Fn0 has a non-empty interior. So I'm going to be able to insert an open ball in this set Fn0, and what I'm going to do is take the open ball around 0b, and x plus b for a given x will be included in Fn0. But Fn0 is a vector space, so by linearity what we're going to have is that negative x plus b will also be included in Fn0. And because of this, when I add x plus b and minus x plus b, then what I'm basically having here is that b will be included in Fn0. So what I end up having is that 0 is an interior point of F because I just built a neighborhood of 0 which is included in Fn0. So 0 is an interior point of Fn0. But if that is the case, then Fn0 will be X, which is not possible because Fn0 is a finite dimensional space, while X is an infinite dimensional space. So it is not possible. This is a contradiction. Therefore, what I'm saying is that if I suppose that X is a countable, has a countable algebraic basis, then I get have a contradiction. So that proves that X admits no countable algebraic basis. And this proof is based on this proof here on this reference. So here's a reference where the proof is from the origin of the proof. Okay, so that was again a proof to, basically stated that if X is an infinite dimensional Banach space, then I am not able to find a countable algebraic basis. Now let me address a question regarding Lax-Milgram. And the question is it possible to generalize Lax-Milgram? In other words, is it possible to have weaker hypothesis on Lax-Milgram? For instance, would Lax-Milgram work if F was not linear? Well, the answer is there are weaker versions, actually stronger versions of the of the theorem with weaker hypothesis. And yes, it is possible in certain cases to have weaker hypothesis. If, for instance, you don't have linearity for f, well, you will still have to have some hypothesis on f and a, but there are cases, there are, versions of the theorem where you can weaken the regularity, the hypothesis. And actually, there is ongoing research in math right now, and quite a few papers that are being published in journals about this lax midgram, generalized lax midgram. So that was the answer to this question. As always, I would like to mention that we hope you will be submitting your homework by Sunday 11:59 p.m. French time. Please be careful if you are in a different time zone. Last week we had a technical glitch on the platform on Coursera, which is fixed now, but I understand that it was not possible to submit any homework on Sunday evening, so that was a problem, and we postponed the deadline for 2 days. So we're very sorry if you encountered problems last week trying to submit your homework. It will not be the case this week, hopefully. Alright, so that's the end of these office hours. I will see you next week, where we will discuss LP spaces. Videos for week 6 actually already online now. They've been up for a few hours already. And we will be back next week to discuss more LP properties during the office hours in between now and then. I wish you a great week.